In this video, we're going to be treating vectors and scalars. Now, this is actually one of the basic topics in physics, and it is important that you take note of it and you know the basics to it. Now, vectors and scalars cover a wide range of physics, okay? They are used in resolving other aspects other than mechanics, okay? When you go to electrical aspects of physics, you find vectors there, and they have a great and wide application. Okay, now first things first, we're going to discuss the definition of vectors and scalars. Now, what are vectors? Vectors are simply quantities that have magnitude and direction, okay? While scalar quantities are quantities that have magnitude and they do not have a direction. So if, for example, I tell you a quantity and then in that quantity I do not give a direction, simply means that quantity is scalar. Okay, and then when I tell you a quantity and I include direction, simply means it's what now? A vector quantity. Now, knowing this definition will help you differentiate some of the quantities we're having in physics and their relations. For example, when someone talks about speed and velocity, many persons might not know the differences, okay? But the difference between speed and velocity is the fact that velocity is the vector and speed is a scalar. Okay, that's one of the basic difference. Now let me explain why is speed and velocity different. Okay, now if for example I tell you that a boy runs with a speed of 20 miles per hour, okay, or an object moves with a speed of 20 miles per hour. Now I did not include the direction, whether the object is moving towards the east, west, north, south, northeast, northwest, and so on and so forth. Since I did not include direction, it means the only thing I'm having about that object that is moving is the speed, which is 20 miles per hour. Now, what if I was to tell you that the object moves with a velocity of 20 miles per hour due east? Now that I have included a direction, I can now say that the object is moving with a velocity. But since I did not include direction in the first, simply means what now? It is only moving with a speed, okay? So vectors are quantities that have what now? Both magnitudes and direction, okay? Now, some objects can be measured in terms of their magnitude and also what now? Direction. Why some cannot? It's just like saying, what is the mass of this marker? The mass of this marker, let's say it is 2 kg. I will not tell you. The mass of this marker is 2 kg due north. Doesn't really make any sense, okay? Because the mass is just the amount of quantity we are having, and direction should not be included, right? But if I tell you the speed of this marker, or rather the velocity of this marker, okay, when I trace vertically upward is let's say 20 meters per second. Okay, since I've included the direction vertically upward, it simply means what now? It is now a velocity simply because I've included what now? Direction. Okay, now for vectors, there are a few things to take note about vectors. Okay, first things first, I'm going to write some examples of vectors and scalars that are important to take note of. Okay, here are some examples of vectors and scalar. Okay, so for vector quantities, we have quantities like velocity. Okay, we have quantities like velocity, we have quantities like acceleration. Okay, we have quantities like momentum. Okay, we have quantities like impulse, of which it is obvious simply because impulse and momentum, they're having the same formula. We have mass times velocity equals what now? Force times time. Okay, so if one is a vector, the other one obviously has to be vector. Okay, to be a vector as well. Okay, for number 5, we're going to have force, and then number 6, we're going to have weight. Okay, in terms of force, we could have different forces. We have viscosity force, we have frictional force and the likes. Okay, we have normal reaction. Okay, for number 7, I'm just going to include an extra one. We're going to call it drag. Okay, so all these and more of it are examples of vectors. Now, when you go to scalars on the other hand, when you come to scalars on the other hand, you're still going to find quantities like work. Okay, quantities like energy. Okay, work and energy are similar, so you should take note that if one is a work a scalar quantity, the other one automatically should be a scalar quantity. Okay, we have mass. Notice how mass is a scalar quantity, but weight is a vector quantity. Now, for mass, it's a measure of the amount or content we are having in an object, okay? While weight is now the gravitational force that a planet acts or use in pulling an object, okay, towards the ground, okay? Now, weight differs in different parts of the earth, okay, and also in the universe. So if I should measure this marker right here on earth, okay, I could go up in a mountain and it will weigh slightly less, okay. Now mass on the other hand is always different. If this is 2 kg, anywhere I go, whether I go to Pluto, go to Venus, it's still going to weigh an amount of 2 kg, okay. So more examples of scalars include potentials, okay. Potential, like an electric potential or gravitational potential. Okay, you should take note of this. Okay, I'm going to see if I can add a few more. Okay, we have speed, and we have distance, and then we have time. Okay, more and more of these guys, okay, can be found. Okay, vectors and scalars. Now the truth or the beautiful thing about vectors and scalars is you cannot resolve any scalar using the rules we have in vectors, okay, but in vectors you can resolve all of it. That is why you notice that there are sometimes when you plot graphs of these guys, you notice that when these ones are having angles, you can resolve them either to the vertical or to the horizontal. These ones on the other hand, you cannot actually resolve them, okay. We cannot resolve them. Why is that? Simply because they are what now? Scalars, okay. We can only find their vectors because they don't have direction. It means we cannot what now? We can only find their magnitude rather, not vectors, simply because they don't have a direction, okay. For these ones they can have what now? Directions. Now next thing we are going to talk about before we go into what we call resolution of vectors is what we call the equilibrant and the resultant vector. So I'm going to come here on our right, equilibrant and resultant vector. Okay, what is an equilibrant vector, what is a resultant vector, and what are the differences between these two guys? Now, a resultant vector is simply a single vector that will act as two or more vectors acting on a body. Here's what I'm saying. Let's say we're having 5 persons pushing a table, okay, in different directions. Some have some are powerful than the others. That is, they are having more strength to push the table than the others. Let's say one person has a force of or one person is applying a force of 100 newtons, another person 15, another person 20, another person 10. Okay, notice that the table wants to move in the direction of the larger force. Okay, but if they are pushing it in different direction, it might not be in the exact opposite direction of the person with the greatest force. Okay, it might move slightly away from where the person with the force of 100 newtons is pushing. Okay, so in the end you notice that when the several forces have been applied to the table, in the end it moves in a direction, okay, with a particular force. It might not still move with 100 newton, okay, but we will know it's going to at the end move in a particular direction with a particular force. Okay, now that particular force that is going to move with is the resultant force, the same way we have a resultant vector. Okay, why we call it resultant vector is simply because it must not be a force. It could be velocity acting on different objects. Okay, it could be impulse or momentum or acceleration acting on different objects. That is why we call it what now? The resultant vector. So the resultant vector is a single vector that is going to act as multiple vectors that are acting on a body. Okay, so that resultant vector, we can choose to replace it with those several vectors. Okay, so the same way, if we're having different forces acting on a table, we can choose to what now? Replace the force with what now? The resultant force in the same direction, and we'll get what now? The same effects. Okay, that's what I'm trying to say. Let's say we are having a table like this, and Mr. A is pushing it from here, Mr. B is pushing it from here. Let's call this Mr. B. Let's say Mr. C is not pushing it towards the right, but rather something like this, Mr. C. And then let's say Mr. D is pushing towards the left, exactly towards the left, Mr. D. Okay, you cannot tell me that the table is going to move in this direction or any direction. You have to solve first. That is what we call what now? That is what we call resolution of vectors. So let's say this is 100 newtons, Okay, this 50, this 30, this 20. Okay, the table doesn't really have to move in this direction simply because there are other forces opposing it and there's one moving here. Okay, it could as well maybe move in somewhere towards the right or this way and the likes. Okay, we just have to find out by resolving. So what we're saying that in the end, after these different persons, Mr. A, B, and C, are applying forces to this table, pushing it. Okay, in the end, the table is going to move in a particular direction. Let's say in the end, after everything, the table now moves in this direction. Okay, with a force of, let's say, 30 newtons in the end. It moves in direction with a force of 30 newtons. It means if all of these persons are pushing this table in this direction, the table is going to move in one direction, right? And with a particular force. The same way, if I just come directly and apply a force of 30 newtons on this place, I'll get the same thing. Okay, in the same direction, the same effect that all of these forces produced on this table is what I'm going to get here. Okay, so that's a simple trick. Now, resultant vector, let's say we're having two vectors acting like this. Okay, let's say we're having two vectors acting like this, one in this direction and another one in this direction. Okay, let's say this is vector FA and this is vector FB. Okay, now the resultant vector is a single vector that will act as if we are to remove this 2 and simply replace it with the single vector, right? So that is the resultant vector that we're going to have. In that case, let's say the resultant vector we got is this guy. I'm going to call the resultant vector R in that direction. Okay, so this is going to be what now? The resultant vector. How about equilibrant vector? What is the difference between equilibrant and resultant vector? The equilibrant vector, take note that it has the same magnitude as the resultant vector, but in opposite direction. There's something called Newton's third law. Okay, in every action there's an equal opposite reaction, which means if there is a single vector that is balancing these two, okay, that is acting as these two moving in this direction, it means there's also going to be a vector that will oppose this motion, okay, or rather balance it. In that case, it means we are going to have another vector in this direction. Now this vector we are going to call what now? The equilibrant what? Vector. Okay, so when you notice that it is exactly opposite in direction. If this one is going towards the east, it means this one will go towards the what now? West. If this one is going towards the north, this one will go towards the what now? So it's always what now? Opposites, but equal in magnitude. So take note, okay, you are going to take note that equilibrant vector, okay, is equal in magnitude, okay, so the resultant vector, okay, but opposite in direction. Okay, they are equal in magnitude but opposite in direction. So let's say the resultant vector after solving we obtained a value of 20 newtons. Automatically, if they ask you find equilibrant vector, it means that this one is what now? 20 newtons. But since the vector, remember we must have direction, right? So let's say this one after solving the direction is, let's say due east. What automatically becomes the direction of this one? Okay, sometimes we put minus to show that it's opposite in direction to this. Okay, what automatically becomes the direction of this guy? Automatically, the direction of this guy simply now, because this one is due east. Okay, opposite of east in the other direction is what now? West. It simply means that what now? This guy is due west. Okay, that's simply what it means. Okay, so if the resultant vector is 20 newtons due east, automatically equilibrium vector is what now? 20 newtons due west. I've seen situations of exams whereby they ask for equilibrium vector, okay, but people solve for resultant vector, you get the same value, 20 newtons, but when they include the direction in the option, that becomes a problem simply because the equilibrium vector will not be due east, but rather it will be what now? Due west in the opposite what now? Direction. Now let's now talk about how we resolve vectors in general. Okay, resolution of vectors. Resolution of vectors. Now, under resolution of vectors, I'm going to break it down into a few parts. Okay, I'm going to talk about when vectors are perpendicular. Okay, when vectors are perpendicular. Okay, and then I'm going to talk about when vectors are acting at an angle to each other, okay? At an angle to each other. Okay, when vectors are perpendicular and when vectors are acting at an angle to each other. Now, how do we solve problems like this? Okay, how do we solve problems like this? First things first, before I go into this two, I would like to explain something real quick. Okay, I would like to explain what we call the Pythagoras theorem that is used in mathematics. Okay, the Pythagoras theorem. Now, this is one of the basic things you learn in elementary maths, okay? And it's something we're going to be applying here. It's quite useful, okay? Now, for Pythagoras theorem, here is what it's saying. When we are having a right angle triangle, okay? This is what a right angle triangle looks like, okay? One of the angle is 90 degrees, okay? We're going to call here, which is the longest side of the triangle, A. We're going to call here B. We're going to call here C, okay? Now, for this triangle, there is what we call Pythagoras theorem that can be applied to this particular kind of triangle, okay? It is saying that the longest side, which is the hypotenuse, when we square it, it is equal to the other side, when we square it, plus the other side, when we what now? Square it. Okay, take note. When we square the longest side, it is equal to the opposite side squared, plus what now? The adjacent side squared. That is what Pythagoras theorem is talking about. So, if it's something you've forgotten, you might want to take your mind back to this guy so you can easily understand how to resolve perpendicular what now vectors. Okay, now let's now go deep into the perpendicular vectors. Okay, so for vectors that are perpendicular, take note. When we say vectors are perpendicular, it means they are acting at 90 degrees to each other. So if the question talks about 90 degrees or perpendicular, it is the same thing. They will also tell you, they could also tell you if they are not 90 or perpendicular, they will tell you that they are orthogonal to each other. Okay, they could also tell you that what now? The vectors are orthogonal to each other. So when you see perpendicular, it means what now? 90. Also means orthogonal, okay? They might also tell you at right angles. Okay, they must also say at right angles to each other. That's another way again. Okay, so whenever you see a question that includes perpendicular, 90, orthogonal, or at right angle, it means what now? The same thing. Okay, simply means what now? The vectors are perpendicular or they are what now? At 90 degrees to each other. So let's say we're having, I'm going to call it one. Let's say we're having two vectors. Okay, I'm going to call this f of x simply because it's on the horizontal axis. I'm going to call it f of y simply because it's on the vertical axis. Now here is a proof that they are perpendicular to each other. Okay, this box simply means 90 degrees. Okay, now take note. To find the resultant vector, it must be a line that is drawn from the intersection of the two vectors. That is, if I want to find my resultant vector, I'm not going to draw a line from this end to this end. Of course, if I do it, I'll actually form a triangle like this and I can apply Pythagoras theorem. I'll get the same magnitude, but my direction will be wrong. Simply because this is not my what now? My resultant vector. The resultant vector must be drawn from the intersection of these two vectors. So take note, okay? If you have to draw the resultant vector like this, it will be what now? Wrong. But rather it is drawn from the intersection of these two vectors. We're going to call it what now? R. Now here is how we solve for the resultant vectors when vectors are perpendicular or at right angles or 90 degrees or they are at an orthogonal angle to each other. Now I'm going to trace here. The reason I'm tracing here to here is because I want to get the length of here, okay? So if here to here is f of y, it means what now? The length of here is also what now? F of y. So can I apply Pythagoras theorem to solve that? Okay, by squaring the longest side, which is r, we can now say that r squared is equal to what is the other side? F of y squared, okay, plus the other side f of x squared, okay. For me, I cannot make r the subject. This means r is equal to the square root of f of y squared plus f of x squared. Okay, that is how it is being done. Okay, so here is the formula for calculating the resultant for vectors that are perpendicular. It is also important to find the direction. Now, how do we find the direction? We are going to bring out this triangle. Okay, we are going to bring out the triangle. Take note of every step I'm taking. We are going to bring out the triangle. Okay, and we're going to draw the box a box at this end. Okay, now here is east, here is west, here is north, and here is south. Simply because sometimes they give you your direction in terms of cardinal points. Okay, we are going to take direction due east, for example. Let's call it theta. That is what we're going to take as a direction. Now, what is the length of here to here? It remains what now? F of y, right? So I'm going to call here f of y, remember, and then from here to here, we're going to call it f of x, because simply what now here to here, we just brought out this what now triangle. Now remember what we call SOHCAHTOA in mathematics. SOHCAHTOA, okay, SOHCAHTOA is an abbreviation for sine of an angle means opposite over hypotenuse. Cosine of an angle means adjacent over hypotenuse. Tan of an angle means opposite over adjacent. Okay, we usually make use of tan in solving for this. Okay, that is why generally you see most materials or books, so just go straight ahead to write tan. Okay, but it depends on the direction we're making use of. Okay, sometimes we might want to make use of 3D bearing, although the ones that are most common are the cardinal points bearing that are being used. Okay, you can learn this more on bearing direction. I'm not going to deep dive into direction. Okay, you can learn more about it in bearing. Okay, there's a video on that as well. Now for this direction, okay, remember tan of an angle is opposite over adjacent, which is f of y. It means tan of the angle theta, or should we call the angle theta or phi? It doesn't really matter, let's call it theta, is equal to opposite, which is f of y, over adjacent. Now to get the angle, we'll take tan to the other side. So we have theta is equal to, when we take tan to the other side, it becomes what we call tan inverse. Okay, so that is tan inverse of f of y divided by f of x. That is how we find the direction, and this is how we find the resultant for vectors that are perpendicular. Take note, it is an easy thing to do. Okay, here is how we find the direction using this formula, and here is how we find the what now, the magnitude. We're definitely going to solve exercises and problems on it. Okay, but before that, I would like us to still understand the other concept before we go deep into solving questions. Okay, at an angle to each other. What about when the vectors are not perpendicular? Okay, in this case, we are assuming that the vector is always at an angle of 90 degrees to each other. What if they're having an angle of 120 degrees? What if they're having an angle of different degrees? Okay, it is something we also have to take note of. Okay, so I'm going to do that. So let's talk about vectors that are acting at an angle to each other. But even before we go into that, there's also something important we need to take note of. Okay, I think I should do that first. Now, how about vectors that are moving in the same or opposite direction? Okay, first things first, let's talk about vectors that are moving in the same or opposite direction. Would there be enough space to write that here? Okay, same or opposite direction. Okay, for vectors in same and opposite direction, okay, let's say we're having a vector here moving in this direction, and then another vector moving in this direction. Okay, let's call this vector b, and let's call this vector a. Okay, so let's come again, a vector moving in this direction, vector a, and another vector moving in this direction, vector b. Notice the difference in the length of the line. Okay, take note, how great a vector is depends on the length of the line. So if you're looking at these two lines, this one is smaller than this. It simply means that this vector has a greater magnitude, but they are moving in the same direction. Look at the direction the arrow is pointing towards. Okay, that's going to tell you the direction. But the length of the line usually tells us how big the vector is. Okay, no specific value. Okay, but I can say this one is 100 newtons. I can say it is 1000 newtons. Depends on what you are given. Okay, but looking at the two lines, we know they can never be what now having the same value, because this one is longer than this. Okay, now take note, when vectors are moving in the same direction, how do you find the resultant vector? Okay, how do you find the resultant vector? To find the resultant vector, it is easy to understand. Let's say we're having a table here, and then I'm pushing it in this direction with a force of 100 newtons. Another person is pushing it on the side of the table in the same direction with a force of 50 newtons. What will be the force that the table will use in moving? It's going to move with our total force, right? So mine is 100, his is 50, so that what now 150. It means we just added what now our total force to get the next force in moving that table, because we are going in the same direction. So in this case, the resultant vector, okay, for vectors moving in the same direction, okay, will be vector A plus vector what now? B. That will be the resultant vector. Okay, so let's say we're having a vector or a force rather of 20 newtons in this direction and another vector of 40 newtons in this direction. What will be the resultant vector? The resultant vector will be equal to 20 plus 40, and that is equal to 60 newtons. It is that easy. Now, what will be the direction? Remember, it's a vector. It is important for us to also find direction. It's a vector. Okay, the direction is still going to remain the same. Just the same way. Imagine, it will sound funny if I'm pushing this table and in the end we are pushing this, but it's not moving now opposite direction. It doesn't make any sense, right? It doesn't make any sense. So it has to move what now? In that same direction. We're pushing in this direction, it's not going to move here. I'm sure if any of you try that and it moves in the opposite direction, you'll be scared. Yeah. Now, take note that for the resultant vector, we are going to what now? Sum both of them. Okay, that's what we're going to do. We're going to sum both vectors to get the resultant. Okay. So in the same direction, we get what now? A plus B. Now, how about this? For different direction, that is opposite direction. No, opposite. Opposite means if one is going towards the left, the other one is going towards the right. I'm not saying when one is going towards the left, the other one will be going upward or sideways or horizontal or diagonal. Okay, I'm talking about opposite, left, right. Okay, that is what we'll talk about in opposite, left, right, up, down. Okay, so for the resultant vector, it is equal to the difference between the two vectors. That is the bigger one minus the smaller one. Why am I subtracting A from B and not B from A? Simply because I'm taking B to be the greater vector. Look at the length of the line. Because of the length of the line, we're assuming B to be what now? The greater vector. So it's what now? Vector B minus what now? Vector A. Okay, and the resultant will be what now? The difference between B and A. What will be the direction? The direction will be the direction of the bigger one. Let's understand this concept again using the table. So if I'm pushing the table in this direction with a force of 100 newtons, the person is pushing the table in my direction with a force of 50 newtons. Because I'm pushing it with a greater force, it means the table has more tendency to move in that direction. But with what force? Because there's another 50 that is opposing it, it means the table is not going to move with 100 force. I'm going to remove that 50 from my own, okay? Which means the table will not be moving with the remaining 50, okay? The table will move in my direction with the remaining 50 because I'm greater, okay? So this vector is going to move in the direction of B because what now? B is greater, okay? But with what value will it move? It will move with a value that is the difference between A and what now? B. Let's say we're having an example. Let's say we're having a vector of 20 newtons in this direction and another vector of 15 newtons in this direction. Notice the length of the line to show that B is actually greater than A. Okay, so the resultant vector will be the difference. That will be 50 minus 20. So resultant vector is 30 newtons, and that is how it is being done. In what direction? In the direction of B. Okay, that's simply what it means. Okay, so for vectors moving in the same and opposite direction, you should know how to tackle it. Okay, now let's go back to the next one, which is at an angle to each other. At an angle to each other. Before I do that, let's explain what we call the concept of cosine and sine rule. Okay, it is important to take note of the concept of cosine and sine rule. Okay, now cosine and sine rule are used in solving for sides and angles for various triangles. Okay, that is the basic use of cosine and sine rule. I'm going to show you how it is being done here. Now, let's say we are having two vectors acting like this. Okay, two vectors acting like this, and let's say in the end they form a triangle. Let's say a triangle like, okay, let me redraw this whole diagram. Okay, let's call these angles, let's call this one alpha, let's call this one beta, and let's call this one gamma. Let's call it A, let's call it B, and let's call it what now? C. Now if you are given a triangle like this, how do you find any of the side that is being given? Okay, or let's say we are giving three sides, we're giving just A and B, we want to find C, or we are giving the angle here, we want to find this and the likes. Okay, we just have to apply what we call cosine rule. So if you don't know cosine rule, I advise you also study this. These things will help in physics. That is why, as whether you're in biological sciences or life sciences, if you're offering physics, it is important to have a good and in-depth knowledge of mathematics, okay, because it will help you do well in the calculations. Okay, so I'm going to talk about the cosine rule. I'm going to talk about the cosine rule. Now, for the cosine rule, it says the square of one side of a triangle the square of one side of a triangle is equal to the square of the other side, b squared, plus the square of the other side, c squared, minus 2 times the product of the other side, b times c, okay, cosine of the angle opposite to the side we are solving for. What do you have here? Gamma. I'll rephrase again. Okay, when we square the side we are looking for, it's going to be equal to the other two sides. When we square them and add them, okay, minus 2 times the product of the other two sides, then cosine of the angle that is opposite to what we are looking for. Which means if we are to solve for b, for example, it's going to be what? B squared is equal to the other side, a squared, plus what? C squared, minus 2 times a and c, since we're looking for b, okay, a times c, cosine of what is the angle opposite b? That's what now? Alpha, cosine of alpha. Okay, similarly, if we're having c squared, if I to solve for c, to be c squared equals what now? A squared plus b squared minus 2 times a and b, right? A times b, okay? Cosine of what is the angle opposite to c? That's beta, okay? Cosine of what now? Beta, okay? It is that easy. Now, also, sometimes we make use of the sine rule, okay? We make use of the sine rule to solve for directions, okay? We make use of the sine rule to solve for directions. Now, here's what sine rule is saying. It's saying a on one side of a triangle divided by sine of the angle, okay? So we have a divided by sine of the angle opposite it, which is gamma, is equal to b divided by sine of the angle opposite it, which is alpha, and is also equal to c divided by sine of the angle opposite it, which is what now? Beta. These things are useful and you can understand them by practicing several problems with them. Okay, we're going to be solving quite a few, but still you need to do more yourself in order for you to understand how these things work. Okay, now I just gave you the basic concept of cosine rule. Now we're going to apply this cosine rule in this next statement, which is at an angle to each other. When vectors are acting at angles to each other, how then do we resolve the issue? Okay, let's say we're having a vector like this and a vector like this, and they are acting at an angle of theta to each other. Now, the only way we can resolve this vector is by applying what we call the parallelogram law of vector. Okay, when vectors are having angles that are not perpendicular, okay, that doesn't make it perpendicular. So I'm going to come here, and in general, I'm going to talk about the parallelogram law of vector. Okay, parallelogram law of vector. Okay, now let's talk about the parallelogram law of vector. The parallelogram law of vector is saying that if I have two vectors, okay, such that the two vectors can represent the side of a parallelogram. Here's what the parallelogram look like. This is what the parallelogram looks like. Sorry, let me make it of equal length. So if here is A, here is also A, here is B, here is also what now? B. Here and here they have equal lengths, here they have equal lengths, and we have a diagonal. Okay, now the parallelogram law of vector is saying that if we're having two vectors such that the sides of the, or rather the two vectors represent the side of a parallelogram. Okay, so if we notice that the two vectors they can be represented by the side of a parallelogram, then the resultant vector is given as a line drawn from the intersection of the two vectors. It means the resultant vector will be the diagonal. That's what it's simply saying. So it's not a definition you have to cram. All you have to do is understand the concept. Remember I said initially that to get a resultant vector, it must be drawn from the intersection of the two vectors. It is because of this what now? This rule. So take note, the parallelogram rule or law of vectors simply says that if we're having two vectors such that they represent the adjacent side of a parallelogram, then the resultant vector is given by the diagonal of the what now? Parallelogram, and this is the what now? The diagonal. Okay, so let's see how we can resolve and get a formula for solving the resultant vector. Okay, so let's say this is the vector and want to resolve it. Let me redraw the whole diagram. So we're having something like this. Okay, and then we're having something like this. Let's say this is vector A and this is vector B, and they're having an angle, okay, theta to each other, okay? So I'm first going to complete the diagram. The first thing I'll do is draw a parallelogram out of the vector. So I'm going to come here and draw a line like this. From here to here will be same as here to here, which is what now? B. And then here to here will be same as here to here, which is what now? A. Now the resultant is what I'm looking for. So it's always going to be a line that is touching two edges, making the diagonal. Okay, this is going to be the resultant. Okay, now by having the resultant, it simply means there's an angle. Take note, this diagonal line might not be splitting this angle into two equal half. Take note, because I know some persons might think, okay, if we're having 30 here, after doing the diagonal, it should split it into two. Okay, it will not be 15, 15, which means it's not 15 to this place. No, it doesn't work that way. You still have to solve what now for the direction. That is why I explained cosine and sine rule, because they are also going to be used in solving these problems. Okay, so if here is vector B, vector A, we're now going to bring out this bottom triangle to solve it. Okay, I'm going to bring out the bottom triangle, of which we're going to be having something like this. Okay, in the bottom triangle, here is A, here is B. Okay, let's call the direction phi. Okay, and this is the resultant. Okay, so this is the resultant. Okay, now remember, or we notice rather, that this one is not looking like this. Okay, to find the resultant, we can make use of any of this formula, but remember, it must need the angle that is opposite. If here is arrow, it means it's also going to need what now? The angle that is here. Okay, so I don't know the value of this angle here. I don't know the value. What am I going to call it? Let's call this one phi instead. Let's call the angle here phi instead. Okay, let's call it phi. And this one, we can give it a different name later on when we get to the direction. Okay, let's call the angle here phi. The reason I'm putting an angle here is because I don't want to solve for r. Now look at this. When I want to solve for A, I needed the angle opposite it. When I wanted to solve for B, I needed the angle opposite it, alpha. When I wanted to solve for C, I needed the angle that was opposite C, which is what now? Beta. It means that I'm going to solve for what now? R. I'm going to need the angle that is what now? Opposite to it. Okay. Now to solve for R, I'm going to make use of the cosine rule. It means that what? R squared is equal to the other two sides squared, A squared plus B squared minus 2 times A times B. Okay, cosine of the angle opposite to R, which is what now? Phi. This is a formula we're going to be making use of. It's not something you should cram, it's something you should what now? Understand. And you can understand this by solving several problems on it. That's the only trick. Okay, the trick to understanding these guys is to what now? Solving several problems on them. Okay, that's the trick to understanding these guys. Now we just brought out a formula for solving the resultant. Okay, when vectors are acting to each other. Now, how then do you get the value of phi? Because the question is only going to give you the angle between the two vectors. Okay, A and B. Okay, A and B. That's what the question is going to give you. It's only going to give you the angle between the two vectors. They're not going to give you phi. How then are you going to get phi? Now, there is a trick to getting it. That's also in maths. Now, observe something. If I should extend this line, I'm going to get a straight horizontal line. Now, this line, this whole angle, the angle between A and B remains theta, right? Okay, but in mathematics, when we're having angles like this, okay, we call them corresponding angles simply because this line is parallel to this line. Okay, these two lines, they are always parallel to each other. If we choose to trace them, they will not meet. Okay, this angle is corresponding to this. That is what we call what now? Corresponding angle. And here we're having angle on the straight line. So what will be phi? It means phi plus theta will give you what now? 180. So what will be phi? Phi is simply what now? 180 minus theta. So we have 180 minus theta. That will be the value of what now? Phi. So I'm going to note that what now? Phi is equal to 180 minus theta. Take notes. Now why I'm asking you to take notes is because when you are given a question, I am only giving the angle between the two vectors. To get the one you are going to use to solve, subtract the angle that is given to you in the question from 180 and use it to solve in this formula. Some person make the mistake of using the angle here to solve. It is wrong. Do not use it. Okay? There is a formula when we want to use it here. So if I choose to put phi instead of so if I choose to put 180 minus phi instead of this place, 180 minus theta rather, instead of phi in this place, I'm going to get a whole different formula. But most times I don't like doing it simply because it creates more confusion. Okay, if I choose to put it in here, it will create more confusion. Okay, let's do it anyways. But if you know you get confused, what you should do is end here. If you know this next thing I'm going to write here, it will confuse you. I'll advise you to what now? Stop here. If I choose to put phi as 180 minus theta into this equation, I'm going to get r squared is equal to a squared plus b squared minus 2 times ab, okay, cosine of what is phi 180 minus theta? 180 minus theta. Now you should take note that the cosine of 180 minus theta, anytime you solve for this on a calculator, you put an angle here, okay, and then you press cosine of 180 minus that angle, your answer is always negative, okay. It is the same as solving for minus cosine of just the angle, okay. Take notes, okay. Like I said, all these are done in trigonometry, it's maths. So if you get confused in this place, you might just want to maybe move the video forward this a little bit to the next part, okay, rather than just confusing yourself with all this, okay. You can just stop here. These two formulas are okay for you, okay. So if I put this in here, I'm going to get r squared equals a squared plus b squared, okay, minus cos theta. If I put it here, the minus can multiply on to give you plus, so you have 2ab cosine of theta. So notice the difference that when I use theta, which is the angle given in the question, here is going to be a plus. That's the trick, okay. So if I'm using here as a plus, it means I'm going to use the angle between the what now, the two guys that is given in the question, okay. But if you know you are going to make mistakes, because this is not cosine, cosine has a minus, okay. If you know you are going to make mistake, instead of learning this one, just understand what I explained here. The angle you are going to use to solve, subtract it from 180 before putting it into the formula, okay. It is that easy. Now how about the direction? To get the direction, we are going to make use of sine rule. So let's say this one is phi, let's call this one delta, and let's call this one, what should I call this angle? Let's call it alpha. Okay, so I can make use of sine to get this angle. Usually, to find the angle, we are going to say, okay, the resultant vector r is at an angle to vector b. So let's say we solve for delta as 30 degrees. So we're going to say the resultant vector is at an angle of 30 degrees to what now? Vector b. See the angle between r and what now? B. Okay, it is that easy. So I can come here and apply the sine rule. Okay, the sine will stay on the board, which is what now? R divided by sine of the angle opposite it. We're going to get sine phi equals a divided by sine of the angle opposite it, that's sine delta. Okay, equals b divided by sine of the angle opposite it, that's sine alpha. Okay, so take note of all of these. These are what we use in resolving vectors. Okay, we're also going to talk about coplanar vectors on a different video. Okay, but for now we're going to solve basic questions on vectors and also on examples of vectors and scalars. We're going to be solving the next video, and here we go. Okay, we're going to be solving some of these problems on vectors on the board. Okay, take note. Now, the first one here says, which of the following are vector quantities? We have work, displacement, acceleration, electric field intensity, magnetic induction. Now, I listed some examples of vectors. Okay, there might be that I did not list some of them here, but answering this question, you should get to know or add them that they are vector quantities. Now, work is not a vector quantity, okay, simply because it doesn't have a direction, okay. Now, displacement, on the other hand, is a vector quantity. Acceleration is a vector quantity. I listed them. And then electric field intensity is also a vector quantity. Now, how about magnetic induction? Magnetic induction, also known as electromagnetic induction, okay, simply talks about the magnetic field, and it also involves a magnitude and direction. So magnetic induction is also a vector quantity. So among these guys listed, 2, 3, 4, 5 are what now? Vector quantities. Now the next question says, which of the following are scalar quantities? Okay, we have torque, electric potential, kinetic energy, and then momentum. Now torque is force times perpendicular distance. This is a vector quantity, okay. Electric potential, remember I said that all potentials are not vector quantities, rather they are scalars, okay. Example, electric potential, gravitational potential, they are what now? All scalars. Now kinetic energy, on the other hand, is an energy or a form of work, okay. So it's a scalar, just like the work we're having here. That is not um a vector quantity. Okay, the question even says, which of the following are scalar quantities? Okay, so which of the following are scalar quantities? Electric potential is a scalar quantity. Kinetic energy is a scalar quantity. Torque is not a scalar quantity. It is a vector rather. Okay, torque is a vector quantity. Okay, Now, how about momentum? Momentum is the vector quantity. Force times perpendicular what now? Distance. These two guys are vectors. These two guys are what now? Scalars. So take note. Now, the next question on the board says, which of the following is a set of vectors? Okay, which of these options contains vectors only? Now, we have option A, weight, displacement, and moment. Weight is a vector, it has a direction. Displacement is a vector. Moment is also a vector. Okay, could be in the clockwise and the clockwise, left or right, what now, or vertical or downward direction. Okay, so these guys, they are what now? All vectors. Okay, option A is the correct answer. But let's review that option. Velocity is a vector, volume is not, and then obtuse is a vector. Okay, density is not a vector, capacitance is not a vector, distance is not a vector. Rather, displacement is a vector, not distance. Okay, and then for this one, mass is not a vector, force is a vector, impulse is a vector. Okay, now over to question 4. The question says, a boy walks 10 meters due west and then 10 meters due south. His displacement is, okay, the problem says a boy walks 10 meters due west. We're going to draw our diagram first. Okay, for question 4, it says the boy walks due west, and west is in this direction. Okay, how many kilometers? Okay, 10 meters due west. Okay, so in the west direction, he walks 10 meters. Okay, and then 10 meters due south. Okay, after walking 10 meters due west, he then walks 10 meters due south. His displacement is, now remember, displacement is the resultant and usually drawn as the intersection, okay, between the two vectors. But take note, if I should draw the displacement as a line coming from these 2 points like this, I will get the magnitude, but I will not get the direction. Okay, why is it? Now take note, there are certain questions that come out like this. If you just go ahead and draw the displacement as the line drawn from the intersection of these two vectors, you will not get it. Okay, your magnitude will be correct, but your direction will be what now? Wrong. Now, the person is going due west and then walks due south. His displacement has to be between west and south. But if I draw it here, here is east, here is south. So we will not be solving an answer that is revolving east and what now? South, which will be wrong. So what I advise most people, for something like this, we are going to draw the west from this point. Okay, that is, we are going to be having a situation like this. 10 meters due west, this is the west. Okay, and also 10 meters due south. This is what now? South. So that in such a way that if we draw our resultant, okay, its value is going to be what now? Be between west and what? South. So for me, I'm going to do the whole stuff. Okay, here is 10 meters, here is 10, so here is also 10. I explained this under what now? Perpendicular vectors. So we're going to solve this using what now? The rule of perpendicular vectors. Okay, this is the point, or the points where the both 10 meters intersect. That is where we're going to be using to get our direction. Now here remains east, here remains west, here remains north, and here remains south. Okay, very, very easy. So we're going to draw this diagram out. We're having a triangle here. Okay, I'm having a triangle there, and this is our direction. Okay, and then we have 10 here, rather we have 10 here, 10 here. Okay, what will be the value of the what now? The resultant. Remember, resultant squared is equal to the other side squared plus the other side squared. That means r squared is equal to 10 squared is 100 plus 10 squared is 100. Okay, so r squared is equal to 200, which means r is equal to the square root of 200. Now, what is the square root of 200 in short form? Okay, what is the square root of 200 in short form? That will be 10 root 2. Okay, that means r is equal to 10 times the square root of 2 meters. That is the displacement. Now, we've arrived at the displacement. Let's now get the direction. How then do we solve for theta? Since there is 10 here is 10, automatically here will be 45 degrees because it's like an isosceles triangle, right? Two sides are equal. It means the angle will also be equal. Okay, if here is 90, here plus here has to sum up to 90, of which here will be what now? 45 degrees. Or let's just go ahead and solve it directly. Okay, remember I said to solve for the direction is equal to the tan inverse of f of y divided by f of x. Okay, so direction is equal to tan inverse of what is f of y, that is 10, divided by f of x, that is 10, and that is equal to tan inverse of 1. Now, it should be used to tan inverse of 1, okay, under trig functions. Tan inverse of 1 is what now? 45 degrees. So theta is equal to what now? 45 degrees. So you can see we also arrived at the same thing. Okay, but to make work easier for you, it is advisable to do stuff like this or get used to the problems that you are solving. So you can tell that yes, 45 degrees even without solving and wasting time. Okay, now 45 degrees, it means here is what now? 45 degrees. Okay, what will now be the direction? Remember, the direction has to be between what now? West and what now? South. So if you go to the options, anyone without west and south should be scrambled out. Okay, all of them are even having west and south. You see jam. Okay, this is a jam problem, and all of them are having what now? West and south. What are we going to do in this case? We're going to get the correct direction with the west and with the south. Okay, now for a direction like this, it is going to be 45 degrees west of south. Here's how I advise students to usually get the answers. Okay, anyone that comes after off, anyone that comes after off, the resultant is going to make the angle with that guy. So you notice that the resultant in this case is R here, right? And it's making an angle of 45 degrees with south, which means if I want to write it, south will always come after the off. Okay, so if for example this was to be 60, okay, let's say here was 60 for example, it would be 60 degrees west of south. If this was 30 degrees, it will be 30 degrees west of south. Okay, after the off, okay, the cardinal point that comes after the off must be the one the resultant is making an angle to. The reason I'm using all these other numbers is simply because when I choose to get the other angle here is 45, so I'm going to get the same thing. So it should be correct to say 45 degrees west of south or 45 degrees south of west when the angle is 45. But when it's a 60, 30, 9, 15, any other angle, it will be wrong to say it that way. Okay, so when we're having 45 degrees west of south, the same thing as now 45 degrees south of west. Okay, now look at the other look at the options here. You notice that they did not write in terms of what now, west or south of west. Here is what we usually do. Now that we've obtained our direction to be 45 degrees west of south, here is another way we can write the direction. We're going to start from the end and write it down to the beginning. So we're going to have south followed by the degree, followed by what now? West. So this can also be written as south, right? Go to the front, 45 degrees. What's the next one? West. So it is also correct to say what now? South, 45 degrees, what now? West. Okay, because it is 45 degrees, you can also have it as west, 45 degrees south. Take notes, because it is 45 degrees, you can write any of these ones first. You can replace any of these ones first. Only for 45 degrees. So take note, if it is 60, we cannot just change it to, we have to write it from the end to the front. Okay, so let's look at the options. South 45 degrees west. Okay, so we have south 45 degrees west. Okay, obviously option C. Now when you check that the degrees of the other ones, they are what now? Different. This one is only what now? One having 45 degrees. So the correct answer to the question is 45 degrees. Okay, that's the correct answer to the question. Okay, that's for number 4. Let's now go into the next question, which is question 5 over there. Now for question 5 says a girl walks 12 meters northward. Okay, let's draw it again. 12 meters northward. So the person walks 12 meters in the north direction, 12 meters northward. Okay, 5 meters eastward, and then 5 meters eastward, 5 meters eastward. Notice how I try my best to make sure the ones with bigger numbers have a longer length. Okay, 5 meters eastward and 7 meters southward. 7 meters southward. Okay, something like this. Her total displacement is, what will be her total or resultant displacement? It is also an easy problem to tackle. Okay, now first things first, this one is going towards the north, this one is going towards the south. Vectors in opposite direction. I explained when vectors are moving in opposite direction, how do you solve the resultant? Subtract the smaller one from the bigger one, right? So 12 minus 7, that's what now 5. In what direction? In the direction of the larger one. So I can come here and replace 12 and 7 as a vector that is going in the north having a magnitude of 5 meters. That's a trick. Okay, assuming there's another one maybe coming in this direction again, I can still subtract it in the direction of the bigger one. Okay, then I'll come here again. There's another vector 5 meter. Okay, given the displacement. Now you notice that the total direction that the vector moves is towards the north and also in the east direction. But if we choose to draw a resultant out of this place, okay, it is going to be in the fourth cardinal point, and our angle will be between west and east, which is wrong because the person moved north more and then east. So the same way we did in the first one, we're going to bring this one and put it up here. Okay, so we're going to be having a new diagram like this, 5 meter. We're going to take this one up, and then we're having another one like this, 5 meter. This one is in the east, this one is in the north. Makes more sense, so that when we draw a resultant out of the point of intersection of the two vectors, it is going to be between what now? North and east. So I can now trace here. Here is also 5. Now this one is similar. We're having the same sides. Okay, just like the one we solved just now. We're having the same sides. We can solve for r. R squared is equal to 5 squared plus 5 squared. So r will give you this is 50. That means r is equal to 2. Is it 2? Or rather 5 root 2 meters. Okay, that's the value of r or the resultant. Okay, what will now be the direction? What will be the direction? The direction here is what now? Theta. Okay, so we have east, we have north here, we have west, and then we have south. Notice that the answers, okay, the answers they give us are in terms of what now? The coordinates. Okay, south 45 degrees west. Okay, so let's solve for it. Origin is 45 because here is 5, here is 5, here is also 45. But we can still solve using the formula tan inverse of what now? F of y over f of x. Okay, is equal to what is f of y? The one on the vertical axis. We have 5. F of x, the one on the horizontal axis, is what now? X. Okay, so tan inverse of that, what are you going to get? Tan inverse of 5 over 5 is 1. What are you going to get? You're going to get 45 degrees. Okay, I'm going to get 45 degrees. That is it. Okay, so here is what now? 45 degrees. So what will be the angle? I explained before. The angle is to the east, which means east is going to come at the back of off. So I can write this as 45 degrees north of east, or I can write it from the back. That becomes east 45 degrees north. Do we have any such option? East 45 degrees north. Now I said something before that when it is 45 degrees, we can write north first. So that is the trick. If it is 45 degrees, we can write this, we can interchange them if it's 45 degrees. But if it is another angle, any other angle like 60, 30, 15, anyone at all, do not interchange. Okay, so we can as well interchange this as north 45 degrees what now? East, which is the one they used in the option. North 45 degrees east. Okay, now 5 with 2 can also be written in decimal, and it is given as 7.07 meters. Okay, so your answer is 7.70 for plus 07, rather 7.07 meters north 45 degrees east. So the answer to question 5 is what now? Option D. Question 6 says, okay, there's a diagram that comes with it. A boat traveled 5 kilometers crossing the canal. Okay, they are saying that from here to here, the boat is trying to cross a canal. You know what a canal is? A river. Okay, and travels 5 kilometers. Okay, from point P to point R. So from here to here is what now? 5 kilometers. The effective displacement of the boat along the PQ. So from here to here, what will be the displacement of the boat? Okay, what distance does it travel in the horizontal what now? Axis. Now what you notice is that the boat was trying to move from probably here to here. But because the river is moving in this direction, the boat will not be able to land exactly here. Okay, but rather somewhere diagonal, okay, or somewhere at a distance from its initial point or its intended point. Okay, that is how boats cross rivers that are moving. Okay, so that is for that. We are going to solve for the effective displacement, and to do that, here to here is TV, that is the length of the river. So we can come here and write it as what now? TV kilometer as well, right? So if we bring out the diagram, what we're going to be having for question 6 will be something like this. We're going to be having something like this. Okay, here is 5 kilometer, here is 3 kilometer, and we have PQ. Okay, here is 90 degrees. Now to do this, remember the trick we used, Pythagoras theorem, the longest side squared. So we are going to have 5 squared is equal to 3 squared plus what? PQ squared. So from here, we can now say 25 is equal to 9 plus PQ squared. So from here, PQ is equal to 25 minus 9, that is 16. So you have square root of 16, which is what now? 4 kilometer. So the correct answer to this question is 4 kilometer. Now, me looking at this question, I already know it's 4 kilometers simply because there's what we call the Pythagoras triple, sides that go together. For a Pythagoras triangle, okay, when we have 3 as one side, 5 on one side, the other side is usually what now? 4. When we have 12 as one side, 5 at one side, the other one is usually what now? 13. Okay, so you take note of those ones that are usually common. Okay, JAM know these things and they tend to bring it in the exams. But if you don't know the trick, you might spend more than the intended time on a question. Okay, another question here says a body of mass m rests on a plane inclined at angle alpha. Okay, here is the plane that is inclined, and you say a body of mass m rests at an angle, okay, to a plane inclined at angle alpha. The components of the weight of the body along the normal. Okay, remember there is always a normal reaction. Okay, there's always a normal reaction that is perpendicular to the surface. Okay, always a normal reaction. And then we have the weight. Here is also alpha. Okay, there's always a normal reaction. Now, this guy is having a weight, okay, that is equal to the normal reaction, right? So if we resolve it, we are closing this angle. Remember, closing of angle makes of course. So if we want to resolve this to the vertical, we're going to what now? Resolve it like this. Okay, if this is the line we're having, we're going to resolve it like this, closing the angle. Okay, now doing that, we're going to make use of cosine, right? What are we resolving? We're resolving the normal reaction or the weight. Okay, so the weight in this case now becomes, or rather, the question even asks the components of the weight and of the body along the normal to the plane. Okay, along the normal to the plane. This is the normal reaction, so we're going to resolve it. Okay, so the normal reaction along the plane will be the weight. Okay, this is the weight, will be the weight cosine of alpha because we are closing it. So the normal reaction is equal to weight is what now? Mass times gravity cosine of alpha. That is simply the answer, which is option what now? Option B. Very, very easy. Okay, now the question 8 here says two perpendicular forces have a resultant of 13 newtons. Okay, if one of the force is 5 newtons, the other should be, I said something before, Pythagoras triple. Okay, if we're having one side as 4 and 3, the other one should be 5. If we're having one side as 5 and 13, the other one should be what now? 12. So obviously our answer will be what now? 12. But let's still solve, okay, and see what our answer is going to be. So they said the two vectors are perpendicular. Let's say these are the two vectors that are perpendicular. Let's say we're looking for the one for y. So we have f of y, and we're giving one as 5 newtons. How do I know this one is 5 newtons? Simply because they said the resultant is 13 and the resultant is drawn like this. Okay, so we have 13. So from here we don't know f of y. So we are going to use Pythagoras theorem, which is the longest side squared. 13 squared is f of y squared plus 5 squared. Okay, so from here f of y squared is equal to 13 squared minus 5 squared. F of y squared is equal to 169 minus 25. F of y squared is equal to 144, and f of y is equal to the square root of 144, which is what now? 12 newtons. Okay, and that is how the answer is given as 12 newtons. Now, to best understand vectors, you also want to solve multiple examination questions that will make it easier for you to understand these concepts.